Input and output are supported by a combination of hardware and software mechanisms. A chain of mechanisms supports an I/O operation. An interrupt allows an I/O device to signal when it needs service. An interrupt vector tells the processor what software should be used to work with the device. A handler provides the software operations necessary to respond to an interrupt. Device priority determines the order in which devices are serviced. Each device is assigned a priority. The CPU keeps track of the priority of the device currently being serviced. If the priority of the interrupting device is higher than that of the current priority, then the interrupt is acknowledged and handled. If several devices have the same assigned priority and interrupt at the same time, a tie-breaking algorithm can be used to determine which one to handle first. The CPU needs to know how to associate a device with a handler. An interrupt vector table provides a set of addresses for the handler supported by the system. When the device interrupts, it provides a vector to the CPU. The vector provides an index into the table that identifies the device's desired handler. This UML sequence diagram illustrates the sequence of events in an interrupt. Software process 1 is executing. Hardware device 1 requests an interrupt. The CPU acknowledges the interrupt. It sets the current interrupt priority level to the priority of the newly acknowledged interrupt, which keeps lower priority devices from interrupting. The vector supplied by device 1 determines the proper interrupt handler. The CPU transfers control from process 1 to handler 1. The handler performs the required operations on device 1. Once handler 1 is finished, the CPU returns control to process 1. The CPU needs to return control to process 1 where it was interrupted. But since the handler is not called by a function call instruction, separate hardware in the CPU saves the required return address. A basic CPU executes only one thread of execution at a time. When multiple interrupts occur, the interrupt mechanism allows one interrupt to stop the execution of another handler and acknowledge the new interrupt. The device priority allows designers to manage when competing interrupts are acknowledged. In this example, device 1 has the highest priority, then device 2, then device 3 with the lowest priority. At the start, devices 2 and 3 interrupt simultaneously. Since device 2 has the highest priority, handler 2 begins execution. While it's executing, device 1 interrupts. It has priority, so the execution of handler 2 is interrupted. Once handler 1 is finished, execution of handler 2 resumes. After handler 2 finishes, device 3 continues execution. During the execution of handler 3, device 1 interrupts again. Because it has higher priority, its handler interrupts handler 3 and executes. Once handler 1 finishes, handler 3 continues its execution. This figure shows how a stack can be used to manage priorities. Here's a UML state diagram for interrupt handling. An interrupt I is asserted and its priority is determined. The priority can be encoded into the IOS device itself and presented at the time of the interrupt. The request priority is compared to the currently executing priority, including the case for which there's no pending interrupt priority. If the request priority is higher than the current priority, it's acknowledged and the interrupt vector is identified. The vector is used to determine a handler address that's used for execution. If the request priority is not higher than the current priority, the set of pending priority levels is updated. RISC-V CPUs use several registers for interrupts and traps, including describing the enabled interrupts, pending interrupts, and associated modes. A hardware error causes a non-maskable interrupt, or NMI. An NMI puts the processor in M mode, and control is transferred to an NMI handler. Thanks for watching.